Okay, so question 18 is a 6-marker, and we're comparing two sets of data for the resistance of a wire practical. That's the one where you change the length of a piece of wire. So I'm doing that just with a crocodile clip, and you move the crocodile clip to different lengths, and then you can use that to calculate the resistance of the wire for different lengths. You can see on here that when the wire is really short, you get a lot of heating happening, and you can see where the rule has been burnt underneath from it getting very hot. So data for shorter wires is not normally very good. The resistance ends up being higher than it should be just because the wire gets very hot. So that's the sort of practical that they did to get this data. So what we're going to do now is compare the two results tables basically from student P and student Q. If you look at the question, so we've got a bunch of data, and then underneath it's actually telling us what we've got to do. So we've got the manufacturer of the wire states the value of the resistance per unit length. So for every centimetre of this wire, it should have a resistance of 1.2 ohms. So this is the value that we are going to be comparing this data to. And we've been asked to compare the data recorded in the two tables. And as well as a sort of general comparison, we've also got to explain which student's data is the most accurate and also the most precise. Okay? So in order to access 6 marks, we need to do a comparison of both tables and the different sort of features of the data in each, whilst also explaining which set of data is more accurate and precise. So for comparison 6 markers, it's a really good idea just to draw, arrange your work as a table. You don't need to be writing a sort of essay to answer this question, and actually when you're comparing two things, it can be really helpful just to do that in a table. So that's how I'm going to answer this one. So I've drawn a table here just on the next page, just to give me a bit more space. And so it's a very simple table. We've just got, I'm going to write down the feature that I'm comparing from the two sets of data, and then just a short sort of sentence or a couple of words about student P's data and student Q's data. Okay. So the first feature I'm going to compare is just looking at the range of values that they've used. So I'm just going to write the feature as the length range. And we can see that for the table P, the ranges from 10 to 19 centimetres, which, let's make some judgments about that. First of all, it's a small range. And my other issue with it is that they've only done 3 different values. And the other issue with it is that they've been uneven with their intervals. They've got unequal intervals. They've gone from 10 to 15, then to 19, so up by 5 and then up by 4. So it's not a good set of data. So they've got unequal intervals. So all 3 of these things are going to affect the accuracy of their results. So if we compare that to student Q, we can see that they have a larger range, so they're going from 10 to 50 centimetres. They've used 5 different values, and all of their intervals are equal. So much better set of data already. So let's put their range as 10 to 50 centimetres. They've got a larger range. 5 values, and they've got equal intervals. They go up by 10 each time. So already, before they've even started collecting data, they've selected a much better range of values. Okay, next thing we can have a look at is their repeats. So let's compare the repeats for the two. Let's do a little line across here. So for this one, there's not such a big difference between them really. They've both done 2 trials, so they've both repeated each measurement twice. So repeats, I'm just going to put 2 for both of them. The next thing we can look at is have they calculated a mean value? And you can see for both sets of data they have taken a mean of their 2 trials, which is good. So we can just put a tick for both of those. Okay, the next thing we're going to compare is the resolution. And I'll just explain on OCR how we use the word resolution. What we're talking about is the smallest increment of the measurements that we're taking. So the resolution of the length of wire for student P, well, they've measured that to the nearest centimetre. So the resolution of the length is to the nearest centimetre. Okay. So for the length, it's the nearest centimetre, and I would argue that they could definitely have measured those lengths to the nearest millimetre. So I think they could have done a better job than that. Whereas you can see in the other set of data, they've measured their lengths here all to the nearest millimetre. Okay, so that means they've got a higher resolution for the length. So the length here is to the nearest millimetre, much better. You couldn't really justify going any more than to the nearest millimetre, because if you're just measuring with a ruler, you can't measure smaller than a millimetre. But you definitely could. You can justify measuring to the nearest millimetre. So that's another way that Q is better than P. And then if we look at the resistances, you can see for P, again, they've only measured the resistances to the nearest ohm, whereas here in Q, they've measured them to the nearest 0.1 of an ohm, because they're all to 1 decimal place. Okay, so for the resistance, is only the nearest ohm, whereas for Q, resistance is to the nearest 0.1 of an ohm. So another way that experiment Q is better. The next thing I want to look at is where they've calculated their values for the resistance per unit length. What you want to see in any column within a results table, and this isn't just for this experiment, this is for any experiment, biology, chemistry or physics, within a column you want to have a consistent number of decimal places, and you can see here that in experiment Q all of the resistance per length values are to 2 decimal places. Even if it's got a 0 on the end, they've included that 0, it's significant. Okay. Whereas for experiment P, again, they haven't been consistent. So they've got 1 decimal place for these two and then 2 decimal places for that one. So they should all be to the same number. So if that was 1.60, they should have included, say, a 0 at the end. So those zeros should be there. They must be to the same number of decimal places. So how do we put that in our table? I'm going to call that the might just call that the decimal places of the resistance per length. And for experiment P, they've been inconsistent. And they've gone from 1 to 2 decimal places, whereas Q is consistent. and they're all 2 decimal places. Okay. Finally, we've done a comparison really of most of the things they've done in the tables. The last thing we haven't actually talked about directly is the accuracy and precision. Well, all of these things are going to help with the accuracy and precision, but there's a little bit more we can say. So let's start by looking at precision. So precision for OCR is defined as being where you look at your sort of final values. It's looking at the range of these measurements. Okay, so all of these should ideally be close together, and it's looking at the spread, basically the range of these values. Okay, and the one which has the smaller range of values is going to be more precise. Okay, so we'd expect this to be a sort of consistent value, and the closer these are together, the more precise the data is. Okay, so I would say that for experiment P, the precision is low, and I'm actually going to quote some values here. So the precision is lower, and the values of the resistance per unit length range from 1.32 to 1.9, so quite a big spread comparatively. Whereas the precision for Q, they're only ranging from 1.0 to 1.2, so this one is almost 0.6 from the smallest to the largest value, whereas in this one the smallest to the largest is only 0.2 of an ohm per centimetre. So precision is higher. Going from 1.0 to 1.2, and it's really important if you've been asked to compare data, it's really important that you actually use specific values in some of your justification when appropriate. And then the final thing is let's compare the accuracy. So precision is the spread or range of your measured values and how close they are together. Accuracy is how close you are to the true value. Okay, so this is where this value of 1.2 ohms that we've got from the manufacturer, we're going to take that as the true value that we're trying to, this is ultimately what we should be measuring here. And it's just comparing how close these are to the true value. And one way you can do that is actually to take a mean value of their resistance per unit lengths across, for here it would be across the 5 and here it would be across the 3, and then seeing how close the mean value is to 1.2. So the accuracy of P is lower, and if you take a mean of these three you get 1.61 mean resistance per unit length equals 1.61 ohms per centimetre, and that's plus 0.41 ohms per centimetre, so it's 0.41 ohms per centimetre larger than the manufacturer value of 1.2. So let's put lower accuracy. And then the accuracy of Q again is better, so higher accuracy. The mean resistance per length for their experiment was, well, when you add those 5 together and divide by 5, you get 1.1 ohms per centimetre, which is only 0.1 of an ohm per centimetre difference. So it's minus 0.10 ohms per centimetre versus manufacturer value. So there's a lot in this one. I mean, we've probably got 10 marks out of 6 here. We've been pretty thorough. But as I said, a really good way of doing a comparison is actually just to put it into a table. Okay, thanks.